In mathematics, a Cauchy sequence, named after Augustin-Louis Cauchy, is a sequence whose elements become arbitrarily close to each other as the sequence progresses. More precisely, given any small positive distance, all but a finite number of elements of the sequence are less than that given distance from each other. Note: it is not sufficient for each term to become arbitrarily close to the preceding term, for instance, does not converge. Rather, it is required for a given n that any pair n greater than n. We have the utility of Cauchy sequences lies in the fact that in a complete metric space, the criterion for convergence depends only on the terms of the sequence itself, as opposed to the definition of convergence, which uses the limit value as well as the terms. This is often exploited in algorithms, both theoretical and applied, where an iterative process can be shown relatively easily to produce a Cauchy sequence, consisting of the iterates, thus fulfilling a logical condition, such as termination. The notions above are not as unfamiliar as they might at first appear. The customary acceptance of the fact that any real number x has a decimal expansion is an implicit acknowledgement that a particular Cauchy sequence of rational numbers has the real limit x. In some cases it may be difficult to describe x independently of such a limiting process involving rational numbers. Generalizations of Cauchy sequences in more abstract uniform spaces exist in the form of Cauchy filters and Cauchy nets. In real numbers, a sequence of real numbers is called a Cauchy sequence if for every positive real number epsilon, there is a positive integer n such that for all natural numbers n greater than n where the vertical bars denote the absolute value. In a similar way one can define Cauchy sequences of rational or complex numbers. Cauchy formulated such a condition by requiring to be infinitesimal for every pair of infinite m in a metric space. To define Cauchy sequences in any metric space X, the absolute value xm, xn, is replaced by the distance d between xm and xn. Formally, given the metric space, a sequence x1, x2, x3 is Cauchy if for every positive real number epsilon greater than 0 there is a positive integer n such that for all positive integers n greater than n, the distance d less than epsilon. Roughly speaking, the terms of the sequence are getting closer and closer together in a way that suggests that the sequence ought to have a limit in X. Nonetheless, such a limit does not always exist within X. Completeness. A metric space X in which every Cauchy sequence converges to an element of X is called complete. Examples: the real numbers are complete under the metric induced by the usual absolute value, and one of the standard constructions of the real numbers involves Cauchy sequences of rational numbers. In this construction, each equivalence class of Cauchy sequences of rational numbers with a certain tail behavior, that is, each class of sequences that get arbitrarily close to one another, is a real number. A rather different type of example is afforded by a metric space X which has the discrete metric. Any Cauchy sequence of elements of X must be constant beyond some fixed point, and converges to the eventually repeating term. Counterexample: rational numbers. The rational numbers Q are not complete. There are sequences of rationals that converge to irrational numbers. These are Cauchy sequences having no limit in Q. In fact, if a real number x is irrational, then the sequence, whose nth term is the truncation to n decimal places of the decimal expansion of x, gives a Cauchy sequence of rational numbers with a rational limit x. Irrational numbers certainly exist. For example, the sequence defined by consists of rational numbers, which is clear from the definition. However, it converges to the irrational square root of 2. See Babylonian method of computing square root. The sequence of ratios of consecutive Fibonacci numbers which, if it converges at all, converges to a limit satisfying, and no rational number has this property. If one considers this as a sequence of real numbers, however, it converges to the real number, the golden ratio, which is irrational. The values of the exponential, sine and cosine functions, exp, sin, cos, are known to be irrational for any rational value of x0. But each can be defined as the limit of a rational Cauchy sequence, using, for instance, the Maclaurin series. Counterexample. Open interval. The open interval x equals in the set of real numbers with an ordinary distance in R is not a complete space. There is a sequence xn equals 1, n in it, which is Cauchy interval, however does not converge in X. Its limit, number 0, does not belong to the space X. Other properties. Every convergent sequence is a Cauchy sequence, since, given any real number epsilon greater than 0, beyond some fixed point, every term of the sequence is within distance epsilon 2 of S, so any two terms of the sequence are within distance epsilon of each other. Every Cauchy sequence of real numbers is bounded. In any metric space, a Cauchy sequence which has a convergent subsequence with limit S is itself convergent, since, given any real number R greater than 0, beyond some fixed point in the original sequence, every term of the subsequence is within distance R2 of S, and any two terms of the original sequence are within distance R2 of each other, so every term of the original sequence is within distance R of S. These last two properties, together with a lemma used in the proof of the Bolzano-Weierstrass theorem. The lemma in question states that every bounded sequence of real numbers has a convergent monotonic subsequence. Given this fact, every Cauchy sequence of real numbers is bounded, hence has a convergent subsequence, hence is itself convergent. It should be noted, though, that this proof of the completeness of the real numbers implicitly makes use of the least upper bound axiom. The alternative approach, mentioned above, of constructing the real numbers is the completion of the rational numbers, makes the completeness of the real numbers tautological. One of the standard illustrations of the advantage of being able to work with Cauchy sequences and make use of completeness is provided by consideration of the summation of an infinite series of real numbers. Such a series is considered to be convergent if and only if the sequence of partial sums is convergent, where it is a routine matter to determine whether the sequence of partial sums is Cauchy or not, since for positive integers p greater than q, if is a uniformly continuous map between the metric spaces M and N and is a Cauchy sequence in M, then is a Cauchy sequence in N. If and are two Cauchy sequences in the rational, real or complex numbers, then the sum and the product are also Cauchy sequences. Generalizations. In topological vector spaces there is also a concept of Cauchy sequence for a topological vector space. Pick a local base for about 0, then if and only if for any there is such that. Technically, this is the same thing as a topological group Cauchy sequence for a particular choice of topology on, namely that for which is a local base. The set of such Cauchy sequences forms a group, and the set of null sequences is a normal subgroup of. The factor group is called the completion of with respect to. One can then show that this completion is isomorphic to the inverse limit of the sequence. An example of this construction, familiar in number theory and algebraic geometry, is the construction of the p-adic completion of the integers with respect to a prime p. In this case, G is the integers under addition, and our is the additive subgroup consisting of integer multiples of pr. If is a cofinal sequence, then this completion is canonical in the sense that it is isomorphic to the inverse limit of, where varies over all normal subgroups of finite index. For further details, see ch. I-10 in Lang's algebra. In constructive mathematics, Cauchy sequences often must be given with a modulus of Cauchy convergence to be useful. If is a Cauchy sequence in the set, then a modulus of Cauchy convergence for the sequence is a function from the set of natural numbers to itself, such that clearly, any sequence with a modulus of Cauchy convergence is a Cauchy sequence. The converse follows from the well-ordering property of the natural numbers. However, this well-ordering property does not hold in constructive mathematics. On the other hand, this converse also follows from the principle of dependent choice, which is generally accepted by constructive mathematicians. Thus, moduli of Cauchy convergence are needed directly only by constructive mathematicians who do not wish to use any form of choice. That said, using a modulus of Cauchy convergence can simplify both definitions and theorems in constructive analysis. Perhaps even more useful are regular Cauchy sequences, sequences with a given modulus of Cauchy convergence. Any Cauchy sequence with a modulus of Cauchy convergence is equivalent to a regular Cauchy sequence. This can be proved without using any form of the axiom of choice. Regular Cauchy sequences were used by Eric Bishop in his Foundations of Constructive Analysis, but they have also been used by Douglas Bridges in a non-constructive textbook. However, Bridges also works on mathematical constructivism. The concept has not spread far outside of that milieu. In a hyperreal continuum, a real sequence has a natural hyperreal extension, defined for hypernatural values h of the index n in addition to the usual natural n. The sequence is Cauchy if and only if for every infinite h and k, the values of infinitely close, or adequal, i.e., where saint is the standard part function.